Good morning, everyone. My name is Jiansong Zhang. I'm an associate professor from Purdue University. So this paper is actually based on a series of developments we have done over the past few years. And these two students, Dax and Merrill, they are students from Mexico. So they have actually research intern with our lab. And then Professor Luis Carlos Félix-Herrán's professor in Mexico, who is their advisor from Mexico. So we have collaborated in trying to further create the physical prototype of the patented Effector that we had for construction robotics functions. So just quickly, the motivation. According to the United Nations, approximately 1.5 billion people between 2025 and 2050 has increased the demand for the housing and the buildings. In the US, currently we're facing a housing shortage, and I believe that's similar in many countries and regions as well. And obviously, the construction industry is notorious for its labor-intensive operations and risk of injuries. For example, there tends to be a lot of manual handling of heavy materials, and there's high rates of accidents and injuries as well. It's usually considered to be risky. For example, the very notorious, famous, we call it a Big Four risk, right, on the construction job site, including struck by, falls, caught in between, and I think electric shock. So according to the OSHA, United States Occupational Safety and Health Administration, there were over 5,000 fatalities in the construction industry, and 20% of those were workplace fatalities, which means people actually died from their jobs. And that was 2022. And then 2024, a more recent data, the Workplace Safety Index, because of the injuries to workers, unfortunately, it has cost our industry $58.07 billion. And also, according to the Associated Builders and Contractors, 70% of the construction companies are struggling to find enough workers. So in other words, we are facing a double problem. So on one side, we are facing the housing shortage, but on the other side, we are facing the workforce shortage. And this is a very good situation, or I shouldn't say good, in that sense, but for our technology development, right? So there is a potential for the implementation and development of construction robotics technology and all kinds of automation to help us address both problems at the same time. Well, we probably all know that a robot can operate on a very precise manner, and they're very efficient. They can operate in a very fast pace. They don't complain. They don't get tired. So the safety risk will dramatically decrease. And in the long run, you may also have cost savings, just because there can be much less injuries and safety risks. And in order to help us to push forward the integration of robotics technology into the construction industry, so we innovate on both fronts. On one front is the innovation in the hardware itself, right? Like, how can we develop new and novel designs of robotic parts and pieces and systems so that they can be better integrated into the construction operations. On the other front, we also need software support, right, for these type of systems. So digital twin, I believe most of us are familiar with this concept. Okay, the idea is that we want to integrate the physical phenomenon with the digital systems to provide real-time back and forth data transfer so that we can perform such tasks such as real-time monitoring, predictive maintenance, training, simulation, or even remote operation. And for us, on this very particular issue that we're looking at, which is about the panel manipulations and the fastening operations, which is a very important operation in building the residential structures in the United States, and I believe in also a lot of other places as well, because most of our residential structures are timber structures. So the idea is that we want to see if we can actually leverage the existing commercial robotic arm, like those heavy industry robotic arms directly for such operations, because they have very high precision, right? And very reliable as well. And a few years ago, we have developed this new end effector, as you can see in the illustration in the figure, that integrates the manipulation, mobilization, manipulation, and the fastening operations of timber panels all into one device. And the idea is that we want to connect this end effector onto any existing commercial industrial robotic arms. And over the years, we also have been refining the design. So we can't, recently we adapted the design to a commercial robotic arm on the market, which is the IRB 7600. And also program the foundations with digital twins, like the software system that can help with supporting the operations. And the software was based on the ROS, for those of us working in robotics, it's a very popular operating system. So methodology-wise, first of all, this is mainly for our students, but they need to understand the project, what is the state of the art, and then propose, how to analyze the design, how to refine the design, so that we can adapt the end effector to the new robotic arm. Okay. In order to achieve that, first of all, you need to set up the environment and have the models ready. So for that, we use the URDF, the Universal Robotics, robot description framework for robotics modeling and simulations. And obviously, we are using ROS, as mentioned earlier. And the programming has been done in RVs. And then after that, we can set up the kinematics using MoveIt is another system. And then we also integrate with Gazebo, which is robotic simulation based on the ROS. And at the end of the day, we want to see what are the conclusions we can get through this process so that in the future, we can also try to implement a similar process to integrate with other robotic arms. So this is a deeper look at the end effector. It, as I mentioned earlier, is a patented design. It's capable of grasping, positioning, and fixing construction panels and combine the electrical and pneumatical components and adaptable for use for other tools. So it's more efficient and economic because it's lightweight and it integrates multiple operations all into one device, so that if you are considering robotics operations, you don't have to have two robots to perform this timber operation. You only need one, so it can save cost. For the coupling system, this is the key to connect. This is the key to connect the existing robotic arm with the end effector, right? So the idea is that we want to design so that it allows for easy separation and attachment. It's like plug and play, cost effective. So at the beginning, we just start with the ABS, plastic, just to try it out. All right. Due to time limit, I will not go through too much detail, but our students have run a lot of analysis in terms of the strength of the material. Can it actually hold the load that is supposed to? And also, our very talented talented students have come up with very innovative design of the end effector so that you can optimize the load distribution so that you do not break these parts too easily. And we also integrated with the digital twin. The first of all, through this, you can perform this kinematics and motion planning because we have the URDF that can be used to describe any existing robot, right? You can model it. It's a classic modeling language. So it's a robot model framework for forward and inverse kinematics. And there is also iterative solver for linear trajectory from start to help us with the target pose analysis. And it's also provided you directly with visualization, which is very helpful for us to understand how the robot can operate. So you can see in this figure, this is one of the visualization that we have in the RV's environment. And we also enable the communication between the digital twin and the robot through the ROS and the gazebo. And this platform can also be used for training the workers who might be working together with the robot so that they understand how to operate. And I believe this is a short video demo. Hopefully we still have time for this. So basically this gives us an idea of how the end effector can operate, how many degrees of freedom it has, and in each dimension, what is the range, what is the load capacity, what are the typical poses, and you can analyze the paths to achieve the target positions, and what kind of operations can be performed. Okay. All right. So because of time, we would like to just show the results now. So we have achieved improvements in the design of the coupling system, which provided greater robustness due to a larger contact area and the better distribution of the stress. And this helps us create the foundations also of digital twin in ROS for our system, but potentially also more broadly for all similar robotics simulation needs. And the coupling system is much easier to attach and detach compared to a previous design from our original patent. And besides the economic way to make it compatible with other robots as well. So this analysis can also help us detect the opportunity in further improvements in the current design. So the idea is that we would like to constantly improve the design in an iterative manner so that it can soon achieve the feasible state for real implementation. So as a conclusion, our end effector promised to be a more economic option in the timber panel operation and fastening operations because it replaced the need for two robotic arms working together. Now we integrate both operations into one end effector, so you only need one robotic arm. And also the proposed tool allows both tasks using just this one robotic arm with our end effector. And we also have improved the end effector design, which will help increase the lifespan of the end effector so that in the long run, it can help you reduce the maintenance cost of the robots because we have redesigned the, if you remember the connector through the stress analysis. So the stress concentrations in critical areas now can be strengthened with, much tougher materials, right? And the deformations caused by the load can be more better handled by the connector. And the implementation in the ROS as a new perspective on the project scope, at the very beginning, we only focus on the hardware itself, but obviously we need a software to support the hardware. And the software system can help us with a faster development process by eliminating the need for a physical robot for this type of iterative analysis. Besides, it's safer because we are just analyzing it in the virtual environment, and it's much faster to change and modify, and we can add more features to the simulation. And there is a potential that I actually broadly call upon our community to consider this type of innovation, right? Because our industry really need it. The automation of placing and fixing the plywoods is a viable solution for addressing the future challenges, but more importantly, we are facing immediate housing shortage and workforce shortage, as I mentioned at the very beginning. So it enables more robust, precise, and secure systems. So we consider to be a significant advance in reducing the production costs and the construction time. Some recommendations based on this particular work. The design obviously can be further improved, right, to further increase the robustness and the function of the system. And also the programming and simulation in RS can be further developed to integrate more functions such as fault anticipation, maintenance support, and also there can be efforts also to try to mitigate the effects of the latency and the noise in the system. Last but not least, the communication protocol is also important. So with the technology advance, there will be more better communication protocols that we can try to incorporate as well. So with that, those are the references.